Hello friends. Today electric vehicle markets are so popular. Demand of electric vehicle stocks are constantly rising because now electric vehicles are the most attractive alternative than gasoline-based internal combustion engine vehicles in order to combat climate change. An electric vehicle or an EV does not have any engine, but it has a massive lithium-ion battery pack that powers the electric vehicle to run. But the main problem of having an electric vehicle or an EV is the time management of its battery charging. Longer charging time may create some anxiety or annoying situation that may impact your trip. Till date, world's fastest charging cars like Tesla Model Y, Audi e-tron GT, Porsche Taycan Turbo, Hyundai Ioniq 5, etc. can be charged up to 80% within 20 to 30 minutes for a trip range of 500 to 550 kilometers. These models are equipped with level 3 charging facility which uses direct current to charge the car's battery via CHAdeMO and combined charging system chargers. Whereas level 1 and level 2 charging facility uses alternating current to charge the car's battery, and they took much longer time to charge the car's battery. Battery stores direct current rather than alternating current. Hence, direct current chargers makes fast charging as it does not require car's onboard rectifier to convert the alternating current to direct current. But still the time management is not at par with the gasoline-based internal combustion engine vehicles. Extreme fast charging is the critical challenge in the adoption of the EVs in the near future. But why we still could not have these fast charging lithium-ion batteries? What are the challenges towards this breakthrough development? Let's discuss in this video. This video could be long, but please watch till the end for some insightful knowledge. In the 1970s, Middle East tensions created an oil embargo, disrupting the oil supplies from the Middle East to the major oil-consuming nations like United States, United Kingdom, New Zealand, Australia, Japan, etc. This compelled the nations to develop the batteries that one could recharge in a very short time and perhaps a fossil-free energy one day. Aggregated efforts of Stanley Whittingham, John Goodenough, and Akira Yoshino made it possible in developing today's lithium-ion batteries. They were awarded Nobel Prize in Chemistry in the year 2019 for their revolutionary achievement in lithium-ion batteries. Today, these lithium-ion batteries are used in electric vehicles and in several other electronic gadgets like laptops, mobile phones, wristwatches, etc. A lithium-ion battery is a rechargeable battery which consists of lithium cobalt oxide as cathode, graphite as anode, and lithium salts like lithium hexafluorophosphate as electrolyte. Graphite, which is used as anode, is actually composed of thin parallel graphene sheets at the molecular level. Within these spaces between these graphene sheets, lithium atoms can be nicely fitted into it. During the charging cycle of the lithium-ion batteries, lithium cobalt oxide releases lithium ions which flows to the graphite electrode and fits within the spaces between these graphene sheets. Whereas during a discharge cycle, lithium atoms within these spaces of the graphene sheets are ionized and flows back to the lithium cobalt oxide electrode. Among other high-quality rechargeable batteries like nickel cadmium, nickel metal hydride, or lead acid batteries, a lithium-ion battery can have a number of advantages. A lithium-ion battery can have a highest energy density as high as 330 watt-hour per kg as compared to 75 watt-hour per kg for a lead acid battery. Hence, lithium-ion batteries are easily transportable. In this connection, let me define milliampere hour or mAh and watt hour or WH. Capacities of the batteries are measured either by mAh or WH. Ampere is the unit measurements of the current and watt is the unit measurements of the power. A 1 mAh battery means that the battery can deliver a continuous current of 1 milliampere for 1 hour before it is totally discharged. Like my phone, it contains 3000 mAh battery. That means my phone can deliver 3000 milliampere current or 3 ampere current for 1 hour before it is totally drained out. If the activities in my phone requires 1500 milliampere, then the battery will last for 2 hours and so on. Similarly, a 1 watt hour battery means that the battery can deliver a continuous 1 watt of power for 1 hour before it is completely discharged. Capacities of the batteries of the mobile phones are usually expressed as milliampere hour, for laptops as watt hour, and for electric vehicles it is usually expressed as kilowatt hour. A 1 kilowatt hour means 1000 watt hours. Lithium-ion batteries are also advantageous because of their low maintenance cost and better life than other rechargeable batteries. In this video, we will discuss 6 main challenges which are the main barriers towards these extreme fast charging lithium-ion batteries. When analyzing each challenge, just keep the charging cycle of the lithium-ion batteries in your mind. That is the lithium-ion's migration towards the graphite electrode. And before analyzing the challenges, we have to know what is a charging rate or C-rate and state of charge or SOC of a battery. 1 C-rate of the battery means that the battery can be charged within 1 hour, whereas 2 C-rate means that the battery can be charged 30 minutes and so on. SOC or state of charge of the battery is the measurement of the amount of energy available for the battery at a specific point of time. If the SOC level of the battery is 90%, that means the battery left 90% energy before it is totally drained out. While charging our mobile phone's battery, we could easily observe that it took much shorter time to charge from 10 to 80% than from 80 to 100%. This is because the charging rate or the C rate of the battery decreases as the SOC or state of charge level of the battery increases. Quite an inverse relation. This is an inherent property of the lithium-ion batteries. All the challenges towards these extreme fast charging lithium-ion batteries to be discussed here would imply to improve the charging rate between this 10 to 80% SOC level of the battery. Challenge 1. Increasing the electrolyte's ionic conductivity. Ionic conductivity of an electrolyte is the electrical conductivity of the electrolyte due to the motion of the ionic charges. So if the ionic conductivity of an electrolyte can be increased, then charging can be made faster. It has been observed that the addition of 20 weight % methyl acetate to carbonate-based electrolyte of the lithium-ion batteries can increase the ionic conductivity by 50%, which eventually lead to the increase of the charging rate to 2 C-rate, the rate we discussed earlier. But during the fast charging, lithium-ion batteries are usually gets heated, and the use of low boiling point methyl acetate will create some serious concerns. Hence, further improvement on this challenge is needed. Challenge number 2. Increasing lithium-ion's transference number. The transference number, also known as the ion transport number, is a ratio of the electrical current that comes from a particular ion to the total electric current in an electrolytic system. This means how well a particular ion conducts electricity in an electrolytic system. And a value closer to 1 means that the particular ion is the primary contributor in conducting electricity. However, in the current lithium-ion batteries, it has been observed that the transference number of the lithium ions are usually below 0.5, and thus improving the transference number of the lithium ions would make the battery charging faster. It has been observed that use of solid electrolytes or polymer electrolytes would increase lithium ions transference number to certain level, and further development on this challenge is needed. Challenge 3. Reducing electrode tortuosity. In a real electrode, ions do migrate into the electrode rather than onto the surface of the electrode. The tortuosity factor is defined as the ratio of the effective length of paths, that is the actual length of a single path from start to end to the medium length. Thus, if the tortuosity of the lithium ions to the electrode can be reduced, then faster charging would be possible. Aligning graphite flakes perpendicular to the anode would reduce out-of-plane tortuosity of the lithium ions. And it has been found by using this method, charging rate can be increased up to 2 C-rate. But we need much greater C-rate than 2 C-rate only, hence much more developments are needed. Challenge number 4. low resistance solid electrolyte interface. The solid electrolyte interface, or ACI, is a layer that is formed on the surface of the electrodes due to the decomposition of the materials from the electrolyte of a battery. The ACI is important for the battery's performance as it prevents further decomposition of the electrolyte, allows lithium transport, and maintains cycling ability of the battery. So if the ACI is made less resistive and more binding tendency towards the lithium ions, then charging rate will be increased. A low resistive ACI made of polyether was made on the graphite anode, and it was found that the charging rate has been increased. Challenge number 5, increasing active sites density on the electrode. Recently, a hybrid anode was made by coating amorphous silicon on the activated graphite. This doubled the reactive surface area, allowed faster lithium ions transport to the electrode, and hence faster charging was observed. Challenge number 6, reducing lithium plating and dendritic formation. Lithium plating occurs when the electrochemical potential of the graphite anode is equal or lower than the potential of the metallic lithium. This means that the lithium ions that arrive at the graphite anode, they cannot distinguish the anode material from the metallic lithium and deposits in the metallic form rather than the desired intercalation within the spaces between the graphene sheets. During fast charging, the high current leads to accumulation of the lithium ions on the graphite anode, and this causes the drop in the electrochemical potential of the graphite anode, resulting in the deposition of the metallic lithium on the graphite anode. Although charging at low temperature causes lithium plating due to the low diffusion rate of the lithium ions, but the serious case of lithium plating occurs when charging is faster. This lithium plating can cause the formation of the dendrites, which elongates from the anode, can even pierce through the separator, reaches cathode, and finally gold, silver, zinc metals can create overpotential to the lithium plating. It has been observed that the lithium plating on the graphite anode can be reduced by coating the graphite anode with the nanoparticles of these metals. In this scenario, an alternate anode design rather than graphite is much required. Thus, these challenges are the major barriers towards having extreme fast charging lithium-ion batteries for today's electric vehicle markets. There are several other issues in full-fledged adoption of the electric vehicle, like the battery's thermal runaway, battery's performance degradation at different temperature ranges, material scarcity, waste management, etc. These topics will be covered in the next videos. Since 20th century, the development of the battery technology was fascinating, primarily due to the quest of the alternate source of energy, and hopefully much more achievements are waiting in the pipeline. Because Bill Gates once said, batteries haven't improved over the last 100 years as much as they would need to in order to make that happen. So I'm invested in a lot of battery companies. Hope you like this video. We will see you in the next one.